Finishing up our discussion on power series, let's look at one more example. Determine the radius of convergence and interval of convergence for the following power series. Now you could use the ratio test here, but since the numerator and denominator are both being raised to an nth power, then it might be easier to use something called the root test. Now the root test has the same conditions as a ratio test. So you can take the nth root of your entire series, or that's the same thing as raising your series to the 1 over n power. So on the next page, let's see what happens. And it's still absolute value. So when we raise both the top and bottom of our power series to the 1 over nth power, well, very easy for us, the n's cancel out. The n exponents cancel out. So we're just left with the absolute value of x minus 6 all over n. Now you can pull the absolute value of x minus 6 out because we're taking the limit as n approaches positive infinity. So when we plug infinity in here for n, well, that's equal to 0, and times our absolute value of x minus 6, our limit is equal to 0. Now, according to the root test, if your limit is less than 1, then it converges. Well, here, what this means is that we no longer have an x, so this means this converges absolutely for every x. So no matter where we are on the number line, it converges everywhere on the number line in the series. So since there's no interval and there's no specific value for the radius of convergence, the radius of convergence is infinity, and our interval of convergence is the entire number line, really, going from negative infinity to positive infinity. So watch out for these special cases.